Hi, Umaya. I think you needed help with G1DI, and G1DI has this graph to plot, and the question here is, looking at this graph, the lines seem to hit each other, and explain how this line of code confirms that the line hit each other, and then get the coordinates of the point where the lines hit each other, right? So I'm going to show you how to do those things. First of all, the plot. I don't have access to the this function right here, axes 3D. I think there's some software associated with your textbook, maybe a file that I don't have, but it's okay. I mean, I can use similar language to plot. I think axes 3D was the way that you guys get this these XYZ axes. So I have drawn this in a different way, but we get the same picture. So we get this is the x-axis here. This is my y-axis here. I've labeled it y right there, and this is the z-axis. I've labeled it z right there. Now, please ignore the red, blue, and green dots here. I drew those in an attempt to solve the problem later on. But for now, just look at the two lines. I have made one of them dashed and one of them solid, just so we could tell the difference between line 1 and line 2. So I just added this statement in here, plot style dashed for line 1. So line 1 is the dashed line, and line 2 is the solid or the thick line. All right, so this is line 1, the dashed line. This is line 2, the thick line. If you rotate this, you could see that they do indeed hit each other. And I've drawn a red dot there where they do hit each other. All right. So the question, however, is why does this line of code tell us, without even looking at the graph, that they do hit each other? And it tells us that they hit each other because there is a solution. So the solution gives us the parameters that define where the graphs intersect. And here's why. The solve function solves an equation, and this is the equation right here. Line 1 equals line 2. So for what s and t does line 1 equal line 2? That's the equation here. Now, the solve function is a function that takes an equation, and this is the equation. And it also, you have to give it which variables we're solving for. So we're going to solve for s and t. So that's why these two things are here. Now, what does the thread function here do? Well, line 1 and line 2 are not just one variable equations. Well, they are one variable equations actually, but they're not scalar equations. These are vector equations, because this is we're dealing with 3D here. So these are vector parametric equations. Let me show you what they are in ordinary language. So line 1 is defined as, now this is what we called point 1 in Mathematica, and this is what we called x1 in Mathematica. This is what we called point 2 in Mathematica, and this is what your homework called x2 in Mathematica. Oh, this is supposed to be s, not t. Okay, so these are the parametric equations for line 1 and line 2. And you cannot solve this just in the usual way, because there's XYZ here, right? So this is line 1 is actually a set of 3 equations. So that's what this is for. That's what this 1 and 2 is for. This 1 and 2 is in, these 1 and 2 are in a bunch of square brackets. There's like 2 pairs of square brackets here. The square brackets mean that we're going to treat these 1 and 2 not as numerals, but as indices, so as position numbers, where this right here, that is position 1. That is also position 1. That right there, that's position number 2. That right there, that's position number 2. And that would be position number 3. That would be position number 3. So the thread function asks Mathematica to apply this equation to each one of these indices. So do this equation for position 1, and then do that equation for position 2. And so here it is. Position 1 of this equation, where we set line 1 equal to line 2, position 1 is, let me just remove the solve and show you what the equation is. All right, so here it is. I removed the solve and just copied everything except for the solve. And this is the same equation. So for position 1, the equation is going to be 1 plus t times 2. That's position 1, right? So there it is. 1 plus t times 2, right there, equals line 2 for position 1. Line 2 for position 1 is 2 plus s. Actually, it's just going to be 2. It's just going to be 2 because this is 0 times s. So it's just going to be 2. So that there it is, equals 2, right? So this is line 1, position 1, equals line 2, position 1, right? And then the thread function has Mathematica apply the same equation to the next position, which in this case will be position number 2. So position 2 is the same as position 1 for line 1 because it's just 1 and 2 here again. So it's going to be 1 plus 2t. But for line 2, it's 2 plus s times negative 2. So 2 minus 2s. So there it is. 1 plus 2t equals 2 minus 2s. So the thread function just takes this equation and applies it to each thing that comes after. Now, we use the solve function to solve those equations. So when you solve this equation for t, you get, let's see, subtract 1 on both sides, divide both sides by 2, you get t equals 1/2. So there it is, t equals 1/2. Now, what about the number 2 equation, this one right here? Well, if you know that t equals 1/2, then 2 times 1/2 is 1, 1 plus 1 is 2, so I can move the negative 2s over this side, so positive 2s equals 2 minus 2, which would be 0. Okay, so then s would be equal to 0, right? And there it is, s equals 0. So the fact that we have a solution, and these are real numbers, means that these lines do intersect. If they didn't intersect, then there wouldn't be a solution. And if the parametric equations were more complicated, then, like if they had a square root or something, then maybe we would get imaginary solutions, which still wouldn't be a real solution, which means they still don't intersect. Okay, so so the fact that we have a real solution here means that the lines intersect. That's how we know. And the next question on the problem that you sent me was pin down the coordinates of the point at which the lines hit each other. So I have done that with this red dot. Right now, the way I found the red dot was I solved the equation. So if your s was equal to 1/2 and your t was equal to 0, is that what we had? We had s equal to 0 and t equal to 1/2. Sorry. So s equal to 0 and t equal to 1/2, then okay, sorry about that. Then what do you get? Well, let's do the s first. So the s equals 0, you put a 0 here, and you get just this. So this is the point where s equals 0. And we should, so since these two lines intersect at that point, then we should get the same answer for t equals 1/2. So let's do that. Let's put t equals 1/2 here, and then what point do we get here? We get 1, 1, 1 plus 1, 1, 1/2, 1/2, or 0.5, let's say. Okay, and that is just 2, 2, 1.5. Right? And that is the same point, right? So that means that the intersection point is 2, 2, 1.5. And I have drawn for you a little red dot there. I'm going to sneeze. Excuse me. Here I did. I called it red intersection point. And I drew for you a little red dot there at 2, 2, 1.5. And that's why there's a red dot there, 2, 2, 1.5. And that's how you find it. You just substitute the s into the equation that has an s, and you get a point. It better be the same point as the point that the equation that has a t gives you after you substitute in the solution for the t. Now, the rest of this is the problem problem II. So now in problem II, you have to use the dot product of the two vectors to show to show that they are perpendicular, right? So if you rotate this just right, it looks like these two lines are perpendicular. So to prove that, you can take the dot product, and the dot product should be 0, right? Right now, to choose the vectors, I think there is a really easy way to choose the vectors, but I couldn't think of the easy way, so I found the hard way. I picked a point on the thick line, and I made it blue. And I picked a point on the dashed line, and I made it green. I picked those points by using the line 1 equation and the line 2 equation. I just put some valid value in for the t, and put some other valid value in for the s. Right? So valid values are given here. In your homework, they defined the valid values go from -2 to 2 for t, and the valid values go from -1 to 1 for s. So I just picked some number in there and substituted in, and I got these points. I got a blue point. Oh, I got a point. I colored it blue for line 2. I got a point. I colored it green for line 1. Right? And then to get a vector that is on line 1, I did the red point minus the green point. So what I did there was, so the green point, my green point, which I just got by substituting some point, some valid number in for t, right? It was t, yes, in for t. So my green point was 1, 1, 1, right? And so to get the vector, I did 2, 2, 1.5 minus 1, 1, 1, right? And here's why. The vector 2, 2, 1.5, that's this red point, minus 1, 1, 1, that's this green point, that vector is on this line, all right? On line 1. So that's why I subtracted them. That gives, subtracting these points gives me a vector. And that vector is, oops, so my vector on line 1 is 2, 2, 1.5 minus 1, 1, 1, and that gets me 1, 1.5. So that is a vector. That is a vector on line 1, right? Now, I did much the same for line 2. Now, 2, 2, 1.5 is a point that is on both line 1 and line 2, so I could use it again. 2, 2, 1.5 minus, oops, minus. Now, I need a point on line 2. And to get a point on line 2, I just pick a valid s, some easy s in between, where is it? In between -1 and 1. And I just plug it in to the line 2 equation, and I get a point. And that point, the point that I got was 2, 4, -2.5. That's the point that I use. So 2, 4, -2.5. All right. So then I get a vector, and so the vector on line 2, it would be it would be this vector. So this minus this. So it would be the vector that fits right in there, right between those 2 points, right? So that vector would be 0, -2, +4, like that. So that's the vector. So that's my vector for line 1. That's my vector for line 2, all right? So then now I just dot them. So I asked Mathematica to dot them. So I actually did it here. I did a vector on line 1, and vector on line 2, and then I asked Mathematica to dot vector line 1 dot vector line 2, and I pressed shift and enter, and I got this nice little graph, and I got the answer, which is 0. Nice little 0 there. That's the answer. I mean, you don't have to put it in the same box, in the same cell as the graph. I mean, you can just do it in a new cell, like this, and you can. It's easy to see here that the answer is 0. So that means the lines are perpendicular, right? And the last question, I gives you a different point 1, a different point 2, different x1, different x2, and the line 1 and line 2 equations are much the same, and the parameters for line, the range for line t, for the t variable and the s parameter are the same. It's just a couple of things. I think it's point 2 is actually the different thing. x1, x2, and point 2. I think those are the different things. Yeah, point 1 is the same, but point 2, x1, and x2 are different. So the plot hints that these two lines hit each other. Do they? Now, you can do this, you can figure the answer out in two ways. You can use the vector cross product, so you're going to have to pick some vectors on line 1 and line 2, and then take the dot product. I said cross product, sorry, I meant to say dot product. Take the dot product and see if they, oh, I'm sorry, that's if they are perpendicular, right? So you can use the solve function with the thread function, setting line 1 equal to line 2, and you can see if there's a real solution there. That's one way to see if they hit each other, but I prefer the easy way. So this is what I copied down for your III problem, right? So I'm going to take out some of this stuff because I don't think I have access to that stuff, right? But I'm going to put in here. I want the axes at the origin, so it's called axes origin, right? That's how you do it. Oh, I also want to label the axes with the x, y, z there. I'm just going to stick that into your III problem, since I don't have access to the fancy axes 3D function that you guys are using. All right, axes origin, axes label. All right, so here are the two lines. This is less fancy because I didn't make one of them dash, but that's okay. We could still see it. And I'm going to rotate this until I see every angle. They look like they cross, don't they? Do they cross? Oh my God, look at that. Look at that. They don't cross. These lines do not cross. Trying to trick us. There, I can make it easier to see by removing the axes. Okay, so here are the lines. There are no axes, and let's. Oh, look! They do not cross. The lines do not cross. Okay, bye.